Hello and welcome. If you're new here, my name is Joe, and I rant about the things that I think we need to do to prepare for the coming effects of climate change. If you've been here before, welcome back. In this video, what is the polar vortex and what does it have to do with climate change? So to explain the polar vortex, I have to discuss multiple layers of the atmosphere. So that's where I'll start this video and just go through what all of the layers of the atmosphere are. You can see here in this diagram there are 5 layers. Here are their labels. The Troposphere, Stratosphere, Mesosphere, Thermosphere, and Exosphere. Now the Troposphere is where we are located. It extends from the surface up to anywhere from 7 to 20 kilometers. That's about 4.5 to 12 miles. It's at its highest, or reaches highest into the sky, near the tropics, and is at its lowest at the poles. The troposphere is where all the weather takes place. It's where a lot of atmospheric mixing takes place. And above that is the stratosphere. It extends from the top of the troposphere to 50 to 65 kilometers up, or about 30 to 40 miles. And again, it varies. It varies in height, or how high it extends into the atmosphere, based on where it's warmest or coolest on the planet. And the mesosphere is the next layer. It goes from the stratosphere up to nearly 100 kilometers up, or 53 to 62 miles. The thermosphere, it's called that because the word thermo refers to temperature. Once you get up to the top of the thermosphere, you have molecules that are traveling so fast. It's the equivalent of thousands of degrees. But it's kind of meaningless because they're so spread out that these molecules could travel for half a mile or more before colliding with another one. The air is super, super thin up there. And then above that is the exosphere. This is where the aurora borealis, it will be occurring. This is where most satellites exist. And at this point, the air is so thin, the molecules are actually free to just shoot off into space, and others actually come back and get captured by the Earth's gravity. Molecules are kind of in and out, but they're pretty much non-existent, but they are there. And this basically is the transition from the top of the Earth's atmosphere to the solar wind. So these are the 5 layers of the atmosphere. And now let's take a look at the Earth in terms of how the sunlight approaches it. And here I'm showing the axis of the Earth, the equator, and there's other lines of latitude. These are called the Arctic Circle or Antarctic Circle, are the ones closest to the North and South Pole. There's also something called the Tropic of Cancer and Tropic of Capricorn. You'll see why these lines mean anything at all in a few slides here. So first, this is showing sunlight approaching from the right. Now, because the Earth is a sphere, the light that hits the Earth in the most direct angle is going to be the most intense. And you've probably seen this yourself with a flashlight. If you shine it straight down at the floor, you get a small circle, but it's much brighter than one if you were to shine the flashlight to the other side of the room, maybe 20 feet in front of you. It's spread out over a much larger area. And so yes, it is lighting up a larger area, but it's much less intense at any one given spot. So it's the same thing with the Earth's surface, is because of the Earth being a sphere, at the equator, or wherever the sun is directly overhead, if you imagine sunlight coming in like a cylinder, so you have 2 equal cylinders, one coming in at the equator and one approaching near the North Pole. At the top of each cylinder, while it's still up in space, the cylinder is the same exact diameter. But as that cylinder of light reaches the ground, at the equator, that circle of light is the same size as it was up in space. But at the ground near the North Pole, as you can see here, that light is spread out over a much larger area. So it's the same amount of energy, same amount of solar radiation, but it's spread out over a much larger area, so that translates into not warming up the ground nearly as much. So that's why the tropics are much, much warmer than the poles. Now, what this causes is that the air at the surface near the equator, or again, wherever the sun is directly overhead, that gets heated more than the areas surrounding, so that air becomes less dense and begins to rise. Now it can only go so far, or rise so far, before it then has to start spreading out. In this case, if it started north of the equator, it moves upwards and then starts moving horizontally towards the North Pole. Same thing in the southern hemisphere. And the reason for this is the top of the troposphere. Where the troposphere transitions into the stratosphere, that boundary, air is not allowed to cross, or it's very difficult for air to cross from the troposphere into the stratosphere. The stratosphere is extremely layered by temperature. Stratos means layer. So that makes it very stable. Stable air resists vertical movement. It can move horizontally in any direction, but it resists moving upwards or downwards. And I'll explain this in a different video because atmospheric stability is actually another important concept to understand when it comes to recognizing why the weather is getting more severe due to the changes in our atmosphere due to absorbing more solar radiation from greenhouse gases and so on. So anyway, again, I'll come back to atmospheric stability another time. But anyway, all you need to know here is that there's basically an upper limit as to how far air can travel vertically in the troposphere. So that vertical limit is that boundary between the troposphere and stratosphere. So as it hits the bottom of the stratosphere, it begins to move laterally or northward or southward. It can only go northward or southward so far before it actually then has to move vertically, and it sinks, and in this case then travels back towards the equator, completing the cycle or completing this loop. Now, as the air moves downward, it doesn't just move back towards the equator, it also spreads out towards each pole. But again, it can only move northward or southward so far before it again has to move vertically. So it does so, but this time by moving upwards. And as it moves upwards, it moves back in the opposite direction where it came from, completing that cycle or that loop. But again, as it moves upwards, it doesn't just spread out southward, it spreads out poleward. And then as it reaches the poles, it sinks, and along the surface travels back down towards the equator. So we get these three loops of air, these three cells of air on either side of the equator, or on either side of wherever the sun is most intense. Now, one thing about the atmosphere and the troposphere is the question might be, well, why is there a limit to how far northward the air can travel before it has to move vertically? Why can't it just be one long circulation where it rises over the equator and then the upper altitudes goes all the way to the North Pole or South Pole, sinks, and then comes back to the equator? If we look again at these three different cells and look just at the air that is rising and then moving towards the pole. If we look at this across, all the way as like a band of air all the way across the planet that's rising and then moving poleward, because the Earth is now getting, the radius of the Earth is getting smaller as you move northward. At each latitude as you approach the North Pole is getting smaller and smaller. So you get like a smaller and smaller ring of air that all this air is squishing into. So it literally squishes together as it moves towards the pole, and can only do that so much before it has to move laterally. And so that's why we get these three cells, they're like gears moving in opposite directions against each other. Now, one thing about the troposphere is it's not a perfect circle around the planet. It actually, and as we saw earlier when you briefly saw the layers of the atmosphere, it extends from 7 kilometers to up to 20 kilometers. It extends the highest to its highest altitude over the equator, or wherever the sun is most intense, and it's at its lowest altitude at the poles. So it would otherwise take up this like this egg shape like this. And so here's a better representation of the circulation on a large scale anyway throughout the atmosphere, the way these cells would be shaped. Now, the thing about them being shaped like this is that it then turns the troposphere into something where it's not really egg-shaped. It actually has these wrinkles in them where it bulges out more above this first cell coming up out of the tropics. It's then at a lower altitude pretty consistently across that second cell, and then over the poles it's at its lowest altitude. But there's basically two major breaks at the top of the troposphere as you go from the equator towards each pole. Now, what that means is, or what this causes, is on one side of this break, the air is much colder than on the other side, but at the same altitude. So basically what ends up happening is you get what's called a temperature gradient, or there's a temperature difference across these breaks in the top of the troposphere. So there's something called the Second Law of Thermodynamics that says that energy always has to flow from areas of high energy to low energy. And it only goes in one direction. So heat, for example, travels from areas of high heat to low heat, or areas of high temperature to low temperature. Air travels from areas of high pressure to low pressure. It doesn't go the other way around. So because of this temperature difference at the same altitude, across just a couple hundred miles, it sets up this temperature gradient or pressure gradient. So the air wants to flow from the equator side towards the pole to make up this difference. The heat wants to flow to make up this difference. So this pressure is created, this pressure difference is created, and so the air does actually begin to move. Now, because of something called the Coriolis Effect, which I'm not going to go into detail here, but I'll basically just say, when air moves on a large scale, it gets, on the northern hemisphere, as it moves, it also gets pulled to the right. And the reason for this is just that the Earth is spinning. So because the Earth is spinning, as air moves on a large scale, it gets pulled to the right in the northern hemisphere or to the left in the southern hemisphere with an equal force, equal to whatever force is causing the air to move in the first place. So what ends up happening is, as this air attempts to move in the northern hemisphere, as it attempts to move from south to north at each of these two locations to try to even out this difference in temperature, it creates these jet streams. It creates this stream of air, this concentrated tube of air that goes all the way around the planet. So it doesn't spiral in and then finally get to the North Pole. It actually moves from west to east. So this would be, what you're seeing here would be like a cross-section of this high velocity narrowly focused stream of air at these two different locations in the northern hemisphere and then also in the southern hemisphere. The red ones represent what's called the subtropical jet stream. The blue one is the polar jet stream. Now, where the jet stream is located is a big deal. With the polar jet stream, for example, if you're north of the polar jet, as you can see from this circulation of air at the surface, air is generally moving from north to south, or from pole towards the equator. So if you're north of the jet stream, air is moving into your location from somewhere else where it was colder. So you are now colder than you otherwise would be, because if you're south of the jet stream, they're getting the opposite effect. They're getting the benefit of air moving into their location from somewhere else that's closer to the equator, where it was able to warm up more before then moving towards the north. So again, if you're north of the jet stream, you're colder than you otherwise would be. If you're south of the jet stream, you're warmer than you otherwise would be. So it sets up where the surface where we are, where the cold fronts and warm fronts set up, and why we have weather in the first place. So anyway, another way to look at these jet streams as tubes of air going around the planet would be in this diagram here. And in both the northern and southern hemisphere, they flow from west to east. All right, so now to make things even more complicated, one thing to notice about this diagram is this shows the Earth's axis exactly up and down, or perpendicular relative to the sun's energy. What about and this corresponds to what conditions would exist on the spring or fall equinox, or equal nights. Equinox means equal nights. But what about on the solstice, when the Earth's axis is tilted as far away from the sunlight as it can be? So let's imagine the Earth on the first day of winter for the northern hemisphere, like in this diagram. Now what happens is these three circulation cells in either hemisphere, in the southern hemisphere, they compress, because where they separate, or where the tropical ones begin, where these cells originate, where the air moves northward and then towards each corresponding pole, is going to be wherever is perpendicular to the sunlight coming in, which is at this lower latitude, this other latitude line that's drawn south of the equator is exactly on the first day of winter, or for the first day of summer for the southern hemisphere. The sunlight is exactly perpendicular at that location, so that marks where the air is beginning to flow upwards and begin all these circulation cells. So again, in the southern hemisphere, these three get compressed. In the northern hemisphere, they get stretched out. And what this does to the shape of the troposphere is those wrinkles or bulges also shift along accordingly. And so then what that does is it changes, again, these temperature gradients still exist. It just happens to change where they exist on the planet. So these jet streams end up moving around accordingly. So in the southern hemisphere, during their summer, the subtropical jet and their polar jet move closer to each other and move closer to the South Pole. In the northern hemisphere, the subtropical jet moves further south, and the polar jet moves further south. So for the United States, during the summer months, the polar jet is up in Canada. But during the winter months, it's most of the time crossing much of the United States. And that's why the winter months are stormier, because the jet stream brings these storms along with it. So now let's take a look at the stratosphere. Because the stratosphere does bulge out, but it doesn't actually have the ripples or the individual bulges the way the stratosphere does. But what happens in the wintertime is the stratosphere contains the ozone layer. So the ozone is absorbing, and this was explained in a different video, the ozone absorbs ultraviolet radiation, and because of that, the ozone layer is actually warmer than the surrounding layers, both above and below. So in the troposphere, for example, temperature typically decreases with height. Once you reach the stratosphere, temperature begins to increase with height because of the ozone being warmed by this ultraviolet light that it's absorbing. But in the wintertime, the pole that is facing away from the sun, the stratosphere over that area is in the Earth's shadow. So that area of ozone layer is not absorbing any solar radiation for a number of days or weeks, depending on how close it is to the North Pole. So that area of the stratosphere really cools down. It compresses, so the atmosphere compresses down closer to the surface. And now, so the top of the stratosphere starts to develop a temperature gradient and therefore a pressure gradient, just like with the cause of the polar jet and the subtropical jet at the top of the troposphere. And so because of this temperature gradient that's happening, and again, for the winter months, this will be happening over the North Pole, we get a jet stream at the top of the stratosphere up near the pole. And this, again, I'll show this as a tube of continuous air going around the planet. This is the polar vortex. So all of this just to explain and just to show you that the polar vortex is an upper level jet stream that exists in the stratosphere, and it actually exists year round, but it's really prevalent. It really becomes strong during the winter months when that part of the stratosphere is cut off from seeing any sunlight for a few weeks. So anyway, let's take a look at this from a different angle. When the polar vortex is stable, it's a single ring of air that goes consistently from west to east around the Arctic region. And underneath that polar vortex is where the coldest air on the planet sets up. So there's basically a correlation between where the coldest air is over the pole and where the polar vortex is located, even though it's way up at the top of the stratosphere. Now, because of this vortex or any of these jet streams, because these exist, because of temperature gradients, whenever the temperature gradient is weakened, meaning the difference in temperature across this distance is now less, that particular jet stream will weaken. So if there's warming happening at the North Pole relative to areas further south, the polar vortex weakens, and so when that happens, you go from a stable polar vortex to an unstable polar vortex, where it actually breaks into several smaller rings. Now they all rotate around each other, so it still has the same general motion, of generally moving from west to east around the North Pole. But when it's unstable, it's broken up into several smaller rings, which can actually move southward, and when they do, they bring this ridiculously cold air with it. But if they're moving southward, in between, warm air is moving poleward that otherwise would not be occurring, which is then also going to be contributing to the warming that would be taking place in those regions that is actually the cause of this whole thing, and it can kind of feed back on itself. But anyway, when there's an unstable polar vortex, that is when the polar vortex ends up making its way into the news, making its way into our weather forecasts, because you'll hear about, oh, the piece of the polar vortex is broken free and is heading in our direction, so we're in for some record lows this weekend or whatever. So again, the polar vortex becomes unstable if there's warming taking place at the pole, which is indicative of climate change. Because here's actually what has happened in the last 50 years. If we take a look at what this is showing is the average temperatures from the decade of 2010 to 2019 versus the average temperatures from 1951 to 1978. Where I got this from, I'll put a link in the description to reference the source of this information. But basically what it's showing is that on a global scale, the warming that has taken place across this period of time has mostly occurred in not only at both poles, but at the North Pole. And so what that's going to do is, over time, this is going to weaken this polar vortex. And so we're going to see it more often. Years ago, decades ago, this was a rare thing to occur where the United States was affected by the polar vortex. It did happen, but this is the kind of thing that's going to happen with more frequency. And so this is one of the things that is a sign of climate change. Now, why this is a big deal when it comes to climate change is if the jet stream is weakening, and all these systems are interconnected, so if the polar vortex is weakening, the polar jet can be weakening as well. And since the polar jet stream is also dependent on and is created by a temperature gradient at the upper levels, if that begins to weaken, it begins to be influenced by other things. Like, for example, in the wintertime, and this is especially true on the East Coast, there's a strong temperature gradient at the surface between the land and the ocean. And during the winter months, the ocean gets colder, but 50-degree ocean temperatures is pretty cold, but if it's 10 degrees on land, that's a 40-degree temperature difference. That's a pretty big temperature gradient. And so what can happen is the jet stream, the polar jet stream, if all these gradients are being weakened by warming taking place in the polar regions, this jet stream that normally would shift back and forth from having a north-south component to sometimes being more stable and traveling consistently from west to east. But if it's weakening, it's going to be influenced more by other temperature gradients, for example, the ones that exist between land and sea. And so what that can do to the jet stream, and this can happen year-round actually, because these gradients set up during other months. But anyway, what this can do is the jet stream can then get trapped in the same place for long periods of time. So instead of storm systems coming through with regularity, you can get stuck in a pattern. A pattern can develop where for weeks at a time or months at a time, you're not getting any rain or you're barely getting any rain. And then for other periods, you go through a very wet spell. So on paper, by the end of the year, you may have gotten the same amount of rainfall as in other years. But instead of getting small amounts consistently, you got a whole bunch all at once, then you went through a dry spell, and then a whole bunch all at once, and then another drought. And that's actually very damaging because one interesting thing about soil, I know I'm kind of going off topic here, but just how this all ties into climate change affects everything in the ecosystem. When soil is really dry, as long as there's a little bit of moisture still in the soil, as soon as it rains, it soaks it right up. The ground soaks up that rain really quickly. But if the ground completely dries out, it becomes what's called hydrophobic. It repels water. The water will actually even pool up on it or ball up on it. It takes a while for that surface tension to break and for the water to actually begin to sink into the soil, and then it's able to absorb more. But for a period of time, the water actually just wants to run off. And so it's actually kind of a double whammy where not only has the ground gone without water for a long period of time, by the time it actually finally gets some, it can't even absorb it at first. And so when these things are happening consistently over different regions, this is this is climate change. This is why it is climate change that is occurring, because every aspect of the climate changes just because of one other thing that has changed. In this case, a weakening of the jet streams because of a weakening of the temperature gradient between the poles and the tropics. And that's why you will hear more about the polar vortex in future forecasts. So I'll wrap this one up here. I hope you enjoyed it. If you did, please click like below. Please comment if you have anything to say. And please do subscribe. And thank you for watching. I'll see you next time.